We are now going to apply all that we have learned in this chapter 4 with sinusoids and graphing and solving with these inverse functions. We're going to apply them now to sound and just waves that are all around us. So I hope you find this a little bit intriguing, the fact that we are in a world of waves and we can work with them through mathematics. So objectives are to apply solving equations to harmonic motion and explore sound waves and how they are made and represented. So this is the key objective here, is to understand simple harmonic motion and then now apply our sinusoids to them. So SHM is our shortcut for this. What this basically is anything that moves back and forth can be represented with a model that is a sinusoid. So a sinusoid, again, is just either a cosine or a sine graph. There is another vocab word, periodic. That just means that it's something that it has a repetition throughout. So when you can just graph it repeatedly, we call it periodic. So here are some examples that you can find around the world. I kind of forgot what this one was. Yeah, so that's just a spider for now. Any kind of thing that sways in the wind, such as a bridge, a string on an instrument, any kind of thing that's going to sway. So these ropes, if you take a ruler, slap it, it's going to vibrate too. So these are all examples of something that would experience a repetitive to and fro motion. So our good old Newton, who is involved in many things with science and math, he has one of our most fundamental laws that for every force there is an equal and opposite force. So that brings us to, when we're looking at forces, we can represent things with a resting position, a displacement force, and a restoring force. And a resting position is just when the object is rest at its normal balance location, no force is on it. Displacement force is going to be when you would, for example, take a pitchfork and smack it, and that pitchfork then is going to be out of place, but then it has that restoring force that's going to want to bring it back to its normal location, but it's going to overdo it by Newton's law and bring it to the other opposite displacement. So displacement force is going to move it from one spot, restoring force is going to move it to its equally opposite location. Alright, so here's a little pendulum visual, and this is my pendulum on a string, and what's going to happen is someone's going to be pulling it, and now it's displaced, right? You can see that this arrow, whatever length that is, that's going to be this length right here. Okay, and then we pull it a further length, so the displacement is represented right here. Let's say that it was like back 2 centimeters, now it's back 2 centimeters. This side represents the displacement distance. So then this is when the restoring force is going to take hold on it. Since someone displaced it, and if they let go, now this restoring force is going to start acting back on it. It's going to bring it back to that original spot, but then also bring it past it to an equal and opposite displacement. So these are the equal and opposite displacement forces. Okay. So and this would, of course, continue. Though we do not live in a frictionless world, if we did, this pendulum would technically go on forever. So here are some interesting visuals about vibrations in the air, things that we cannot see, but this video right here puts a actual visual to it that you can see these sounds in action. And here I looked at how things work, and I just want to read this to you because here I go. Every time you strike a tuning fork, you're setting off a tiny, invisible hurricane, thrashing back and forth at tremendous speeds. The two prongs of the fork, known as tines, are smashing against the nearby air molecules, kicking off a chain of impacts that echo through the air. When these violent, microscopic collisions hit your eardrum, your brain processes them as a gentle hum. So that kind of makes it all very exciting, don't you think? Here's that tuning fork, just one of those tines. So if you look at one of those tines, if you smacked it, it's out of place, right? And so there it's out of place, and then it's going back with its restoring force. And so that would just continue for a very long time because of the force that it would take to displace a tine. There's going to be a really strong force to restore it, And when that happens, you get these really quick vibrations that are hard to see. But again, look at that visual that I gave, that YouTube clip, and you will see that. Alright, so these bring us to the main areas of study. When we're studying simple harmonic motion, the speed of the tuning fork's vibration is known as its frequency. So the speed at which it's going back and forth, the number of cycles in a given time, usually a second, is what we define as frequency. Alright, so frequency, how it is calculated, when we're, again, since these vibrations are periodic, they can be represented with a sine or a cosine graph. So now, then, if you're going to write the equation, we're going to be writing it with that y equals sine of, and then 4 pi x, something like that. So what's going to happen is we actually take that b, what was known in our Flippy book as that b, that multiplier to x, that's going to represent or help us calculate our frequency. When we're talking frequency, what we're accustomed to is using the Greek letter omega instead. So you are going to see this used very often when we're studying frequency of any type. So again, it hopefully makes sense that that b affected the period, and that period was the length of time that it would take for some sort of cycle to start repeating itself. So that period was the length of time that it would take to repeat itself. That's what that b helped us find. And so now, if we're going to study frequency, the speed of this vibration, then hopefully it makes sense that we're going to also be using that b. But it's just our period switched around. Period would have been 2 pi divided by b. Frequency is going to be b divided by 2 pi. Okay? Hertz is the unit of measurement for vibrations per second. So that's just the unit of measurement. Once we figure out what that speed of a vibration is, we need some sort of label for it, just like we would have to have like 60. Doesn't make a whole lot of sense for speed, but 60 miles per hour does. So we're going to find a certain amount of frequency or speed of our tuning fork, and Hertz says that this is how many vibrations per second we have. Oops. Just ignore that. Okay, so given the function y equals sine of 4 pi x, what is the period, amplitude, and frequency? This is what we're accustomed to. The period, we would just take 2 pi divided by this 4 pi, and we would have calculated, oh, our period is 1/2. No big deal. Amplitude here is just 1. Okay, and then frequency would be, now, this is our newer one. It's where we would flip the period. It's 4 pi over 2 pi is equal to 2. And so I should have my label Hertz here. So there it is. It's 2 hertz, which means there's 2 vibrations per second. So let's visually, this is what we would have done before. There are no shifts, and we would have easily graphed this. So keep in mind, I went all the way to 2 pi. I really didn't need to do that, because here's the thing. What I want you to look at are these cutoff places. Here would be the 2, right? That's just on Google what they decided the key points were. Okay, so again, we graph these a little bit differently. But here's what I want you to see, that if 2 is there, then here is 1. Okay, and we're going to call these in seconds. The x-axis is seconds right now. So here is that 1 mark. Here would be 1 second. And what I hope you can see is the frequency. There were 2 cycles in 1 second. So that's why we're saying 2 hertz, 2 vibrations in 1 second. The period, how long did it take to reach its final period or its full cycle? Well, it only took 1/2 a second. So here's that. And so hopefully you can see how these are very much intertwined. Period and frequency, whatever the period was, it kind of makes the frequency what it is. And vice versa, pretty much. Alright, so give the equation for a wavelength of frequency 392 hertz and amplitude 1. So if we had a 392 hertz and amplitude 1, can we come up with this y equals a times sine b x? And by the way, you can use cosine just as easily, but typically anything that you strike is going to be starting at its resting point, and then you strike it, and that's what it's going to be. However, you could easily do a cosine, and it would just make as much sense to anyone with that knowledge of sine and cosine waves, because they are technically very much the same. So give the equation for a wavelength at frequency 392 hertz and amplitude of 1. So here's kind of what we have. the period, normally we would say, okay, well, I need this B, right? So we don't know it. So this is where frequency is going to come into play, because like I was saying, since they're so intertwined up here, if you know the frequency, you'll know the period. So at this point we don't know what our B is, so we can't calculate period, but we do know what our frequency is, so we can. And again, that alpha is just, or I'm sorry, that omega is just going to be our B. So when you do this, I'm going to instead incorporate B here instead for that omega, just because we're more accustomed to it. We have B divided by 2 pi is equal to 392, because that's what our frequency was stated here. And so then when you solve for our B, it's going to be 784 pi. So also amplitude is kind of simple here, they just gave that to us. So what we have right now is our B. It's, this should be 1, sorry. 1 sine, and then here was our B that we just solved for. So now we can go back and solve for our period. So our period will be 2 pi divided by whatever our multiplier on our x was, so our B, and so we get about 0.008 seconds. So when you have this right here, think about it relative to what we had up here. Here's our 1. We have 8 thousandths of a second. So if you could separate this into 1,000 pieces, then quarter that, we would have 1 full sine wave for us in that 0.008 of a second. Frequency corresponds to the sound pitch. The higher the frequency, the higher the pitch. Amplitude corresponds to the sound intensity, or in other words, loudness. The higher the amplitude, the louder the sound. An interesting visual for you to see. So every sound that we hear is going to have its own frequency. So here I have the keyboard for you, and if you went to the highest note on the keyboard, what is that? That would be C. It would be the high C, so C8, it would be the 8th octave of C on your keyboard. The frequency would be 4,186, and that frequency is unique only to that pitch. So that's how we hear those different sounds. If you're down here at the lowest A, that's going to be only 27.5 vibrations per second in your eardrum. And just remember, this doesn't apply just to sound waves, it applies to anything that is going to be oscillating back and forth. And here's just a couple different other sites that can visualize these different SHM situations, simple harmonic motion situations.